thing. But yeah, he's a boost. Okay, so we will begin today with trying to do a quick recap of everything we talked about last week to try and bring everyone up to speed as fast as possible. And then we'll finish up what's called propositional logic and move on to what's called predicate logic. So a quick recap through proposition. Now, when I talked to you guys last week, I talked about the statement. I said a statement, did I say a proposition is a proposition? Oh, sorry. No. So here's what I said last time for our definition of a statement. A statement is a sentence that is either true or false, but not both. And the reason I said statement is because the book I recommend uses statement. All modern language says proposition now. So I'm going to switch over to saying proposition. Proposition and statement mean the exact same thing. Proposition is something that's either true or false. A statement is a sentence that's either true or false. They mean the exact same thing. Propositional logic, the reason it's called propositional logic is you're studying the logic you can apply to a proposition or statements. Things that are either true or false. Good with that word proposition? Good? Okay, now we have our 5 basic operators that we use over and over again with propositions. So let's go over each of them one more time with the truth table. Before we say that, remind you of some syntax I use. I'll typically use Greek letters as stand-in for propositions. So alpha will be some random proposition. It could be something like, the sky is blue. Oops. You get the point. So now we're going to apply operations to propositions. So I'm going to start out with alpha here, and then we'll start by looking at what the not alpha is. So this symbol right here, this is the first one we're going to re-go over. It's called the not symbol. So let's rewrite out our truth table for this really quick. So if alpha is a proposition, what are all the possible values alpha can have?
True or false?
True or false. Alpha is some statement, some proposition. Which one? Doesn't matter. All the possible values for that proposition are it's either true or it's false. There is no other possibility by definition of a proposition. A proposition is a sentence that's either true or false, but not both. So these are all the possibilities for alpha. The sky is blue. We typically call that a true proposition. 2 plus 2 equals 7. We call that a false proposition. But they're both propositions. They're statements that are either true or false. Sentences that are either true or false. With me? Okay, so now if alpha is true, not alpha is false. Similarly, if alpha is false, not alpha is true. So that's our first one that we're going to review, the not operator. Not takes true statements and makes them false, takes false statements and makes them true. Good? So let's, where's my eraser? Right here. So let's move on to a reminder of our next little symbol there. Remember what the upside down V was? Which one? And. Perfect. So that is our and operator. So this time we need to, when we apply and, we need 2 propositions. We and 2 propositions together. So I have 2 propositions now, alpha and beta. Those are completely random propositions. We know nothing about them except that they are propositions. Our job is, knowing the truth or falsity of alpha and beta, to determine the truth or falsity of alpha and beta. So we have 2 statements. What are all the possible combinations of values for those 2 statements? We can have that alpha is a true statement and beta is a true statement. We can have alpha is a true statement and beta is a false statement. We can have alpha is a false statement and beta is a true statement. Or we can have that both of them are false statements. These are all the 4 possible combinations. I know that alpha is a proposition. I know that beta is a proposition. Therefore, alpha has to be true or false and not both. Beta has to be true or false and not both. These are all the possible scenarios we can have. They're both true. Alpha is true, beta is false. Alpha is false, beta is true. Or they're both false. Does that make sense? Okay. So now we need to evaluate the proposition alpha and beta. So if alpha is true and if beta is true, then the proposition alpha and beta is true. True and true is true. The example I typically like to use is grab 2 markers, set up the scenario. We'll make alpha the statement, Donnie's holding a red marker. We'll make beta the statement, Donnie's holding a black marker. And so if I'm holding a red marker and I'm holding a black marker, here's the statement. Donnie's holding a red marker and Donnie's holding a black marker, true. Yes, in that scenario, yes. So we just set up this scenario. I made alpha true and beta true. In our particular case, alpha was me holding the red, beta was me holding the black, and alpha and beta was true. So now let's look at the next one. I'm going to set up this scenario. We said alpha is Donnie's holding a red marker. I'm going to make that true. We said beta is Donnie's holding a black marker. I'm going to make that one false. Question, is this proposition true? The proposition, Donnie's holding a red marker and Donnie's holding a black marker.
False.
No, it's not true, so it's false. So this one is false. Set up this scenario. I'm holding a red marker, false. I'm holding a black marker, true.
False.
When you add them together, it's false. And then finally, if I'm not holding either marker, it's true, right?
No, it's false.
No, it's false. If I'm not holding any marker, the statement I'm holding a red marker and I'm holding a black marker is false. That was and. Good on that recap? Any questions about and? Okay. So now we'll move on to our next operator. We'll keep this up. It will be applied to 2, so this will still be all our possible combinations. But the next one we'll talk about is the V-looking symbol. We remember what that symbol is? Or, correct. So this time we're looking at alpha or beta. Okay? And let's go through the scenarios one more time. We'll keep it how it was. Alpha, we'll pretend is Donnie's holding a red marker. Beta is Donnie's holding a black marker. Set it up. Is the proposition Donnie's holding a red marker or Donnie's holding a black marker true?
Yeah.
Yes. Is the statement...
Hold on.
Go ahead.
No.
You're saying it's false. Wonderful. Because this is actually a point that we have a discussion about, but we can actually have it real briefly again. So this or symbol, when we use or in the English language, we have 2 different ways that we use the word or. And to give you an example of how we have those 2 different ways we use the word or, give you 2 examples. So if I were to say, in order to take my class, you have to take physics or calculus, then I mean you can take physics and take my class, or you can take calculus and take my class, or you can take both. And so in that sense, taking both is an option. And we call that the inclusive or. Another example of the way I could use the word or is like what you see on a menu when you go to a restaurant. You order something and it says, and this comes with a side of salad or soup. In that case, when we use the word or, it's understood that you can't have both. They're saying one and not the other, one and only one. We call that the exclusive or. So in logic, we're always talking about the inclusive or.
Or is always inclusive.
This or is, we make a special symbol, this one, when we're talking about the exclusive or.
Perfect.
Or we write it this way. X or.
And that is also a common operator.
Not as much, which is why it isn't in this list.
But I'm going to.
But it is a valid operator, just as valid as any other one.
It's something you would come across.
You could come across it, yes.
Okay.
Okay, so for our definition of or, we accept the case where if both are true, then we say the or is true, the disjunction of them. Okay, next case. I'm holding a red, I'm not holding a black. Donnie's holding a red marker or Donnie's holding a black marker?
True.
True. Am I holding a red or a black?
Yes.
Yes. This one? Am I holding a red or a black?
Yes.
Yes. Finally, am I holding a red or a black?
No.
No. So this is the only case that's false. And then if this were the X or operator, the only thing that changes is this one would have been false. Good? Okay, now the hard one. Implies, the least intuitive of them. Alpha implies beta. Okay, so remember to keep your intuition straight about implies. Alpha is a statement that is always inferent. We're saying that this, each case by case.
When you say implies, is that inductive reasoning or deductive?
Deductive.
So in the deductive sense implies, not inductive.
Deductive reason is by definition a tautological implication. So it's always an implication, it's an implication that's always true.
Yes.
Yes. So in the logical sense, this says inductive reason has no place in propositional and first order predicate logic,
So
which is all we're covering.
It's not
Never in this universe.
Okay, we're
Okay.
never dealing with it.
Correct.
Okay.
Okay, so now, setting up implies, we have alpha implies beta. Alpha is going to be the statement, Donnie's holding a red marker. Beta is going to be a statement, Donnie's holding a black marker. Now, this is going to be the state of the universe forever, always in existence, just me and these markers. This statement is always true, this statement is always false. When that's the case, is a statement, if Donnie's, I'm going to say if then rather than implies, because it flows better in English. So is a statement, if Donnie's holding a red marker, then he's holding a black marker, true.
So this is classical if-then logic.
Correct.
Okay.
So in that case, it's true. Now what if I were to set down the black marker? If Donnie's holding a red marker, then he's holding a black marker. False. Okay, those are the two intuitive ones. Now here comes to the inintuitive ones. If Donnie's holding a red marker, then he's holding a black marker. You don't want to call that true. Your intuition says that shouldn't be true. Ask yourself this question, though, to help equip with your intuition. Is it false? No. So here's my statement. If Donnie's holding a red marker, then he's holding a black marker. Is it false?
No.
Okay, if it's not false, by definition, it's true. That's one way to try and make it appeal to your intuition. The other way you can make it appeal to your intuition is we have a definition for implications like these. We call them vacuously true. Implication is vacuously true if it is impossible to satisfy alpha. If alpha is always false, the implication is vacuously true. Make sense? Okay, and then finally, if Donnie's holding a, can't remember which was which, red? If Donnie's holding a red marker, then he's holding a black marker.
True.
True. So 2 checks for your intuition to help you. First, you can ask yourself, is it false? And if you're saying no, then your intuition is helping you along. If that doesn't help you think, is it vacuously true?
So,
And those 2 thoughts will probably help you keep the
help me
table right.
understand this vacuously true business.
If the antecedent is always false, an implication is always true. Antecedent is what we call this side of an implication. Conclusion is what we call this side.
So if the antecedent is always false, so if it's impossible to satisfy the antecedent, then it is always true.
That's almost a word for word definition of vacuously true. Perfect. So that was implies, the least intuitive of them. We good on that one? Okay. And then finally, we have the logical equivalence operator. Alpha is logically equivalent to beta. Alpha is logically equivalent to beta means alpha and beta have the same value. They're logically equivalent. They have the same value. Do alpha and beta have the same value?
Yes.
In this case, yes. Do they in this case?
No.
No. Do they in this case?
No.
No. Do they in this case?
Yes.
Yes.
Will you say that one more time, what that operation means?
Logically equivalent. They have the same value. Alpha and beta have the same value. They're logically equivalent. Now, one of the proofs we did last time is alpha logically equivalent to beta is also the same thing as alpha implies beta and beta implies alpha. So to see that, you just set the truth table, say that they always get the same values. We won't do that again. But the important part there is every time you see alpha if and only if beta, anytime you hear that kind of language, is saying that alpha and beta are logically equivalent. It's saying alpha implies beta and beta implies alpha. It's common language in proofs. Alpha if and only if beta. Means they're logically equivalent. Means alpha implies beta and beta implies alpha. That's why it's a back and forth arrow, because we're trying to do this one implies this and this one implies this. That's where that symbol comes from. Good? Okay, so those are the basic operations of propositional logic. You can have a lot more operations, but these are the ones we typically work with. Okay, now we also proved some useful little theorems last time, apart from the one I just erased. I don't know why I forgot to put that one on here, but I did for some reason. So good thing I wrote down, but now talking about these three. So these are three useful theorems for helping us just understand sentences or rewording sentences. So knowing that this and this are logically equivalent, or this and this are logically equivalent, or this and this are logically equivalent. It's very common that you're trying to prove some statement, and think about this way is hard, but think about the statement this way somehow makes it easier. Or vice versa. And that happens for all these cases. That's why it's crucial you understand that these are logically equivalent. It's going to help you a lot when it comes to proving things. So let's remind ourselves of the first one. We won't draw out the whole truth table. We'll just say some sentences to help it click in your head. So this one is saying, well, we can just read it. This one says, not alpha and beta is the same thing as not alpha or not beta. If I'm not holding a red and black marker, then either I'm not holding a red marker or I'm not holding a black marker.
The inclusive or.
The inclusive or, yes. From here on out, all or is inclusive. Is that clicking with your intuition? If I'm not holding both, then I'm not holding one or I'm not holding the other. That clicking? This one, if I'm not holding one or the other, then I'm not holding one and I'm not holding the other. If I'm not holding a red or black marker, let's set this up. Well, I don't know if that's, let's think about basically doing a truth table on this one. If I'm not holding a red or black marker, then that means I'm not holding a red marker and I'm not holding a black marker. We need to see that one? Let's just set it up and say the word rather than writing out the whole table. Here's alpha, here's beta. Well, we can write out. We're doing the second one. So we're looking at not alpha or beta, and then we're looking at not alpha and not beta. Sometimes just filling these out helps it quick. So we can have true, 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 false, false, true, false, false. Again, we'll make alpha me holding a red marker, beta me holding a black marker. So I'll set up the scenario, true, true. So this statement says,
I cannot understand how if alpha implies beta, that being equivalent to not beta implies not alpha.
we'll get to that one. We're on this one.
Oh, I thought you finished that, sorry.
Oh, nope. So we're doing this one real quick. Okay. So we have not alpha or beta. So set up the scenario. Donnie's holding a red marker, true. Donnie's holding a black marker, true. Right? So alpha or beta is true. So not alpha or beta is false. With me? I'm not holding a red or black marker. That's false. I am holding a red or black marker. Good? Look at this one. I'm not holding a red marker, and I'm not holding a black marker. False. I just lied to you. Right? So let's look at this one. I say, so set this scenario. I say I am not holding a red or black marker. Perfect. Now look at this one. I'm not holding a red marker, and I'm not holding a black marker. False. I am holding red. Oops. False. Next scenario. I am not holding a red marker. I am not holding a red or black marker. False.
It looks like this inclusive or maybe means the exact same thing as and. I mean, it can't. There's, what exactly is the difference?
So if you want a precise, so here's a precise definition. We come out from language to help it appeal to intuition, but here actually is its exact definition. So true, 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 false, false, true, false, false. True, 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 false. True, false, false, false. So what we call the or, here's what we call the and. Now this table is actually its exact definition. We tried to derive the table from the English language to help it appeal to the language, but this is actually its exact definition. What do we mean by alpha or beta? Here's exactly what we mean. We mean true if they're both true, true if that one's true and that one's false, true if that one's false and that one's true, false if they're both false. And that's actually its precise definition. Because logic is in no way dependent upon the English language. So we try to go from language to the table, but that's backwards from the way you actually derive it. You show the table and you say, and we're going to call that symbol or. And then
from this theorem, it looks like there's quite an intimate relationship.
yes, to distribute a not across an or
Yields an and.
yields an and to distribute a not across an and yields an or. That's correct. Similar thing, well, no, that's different. Should say it. I don't have a better intuition for that. But so here's our exact definitions. And
Okay, I understand.
okay. So setting up the last scenario. So here we are. We said it is not the case that I'm holding a red or black marker. That was false, right? Now look at this one. I'm not holding a red marker and I'm not holding a black marker. False. Wonderful. Finally, last scenario, make it both false. It is not the case that I'm holding a red or black marker.
True.
True. I'm not holding a red marker and I'm not holding a black marker.
True.
True. So here hopefully helps your intuition for this theorem. Now let's move on to this last theorem. Alpha implies beta is the same thing as not beta implies not alpha. And do we remember what we call that? What do we call this? Contrapositive. Good. So we have an alpha, we have a beta, we have alpha implies beta. Let's see, I'm also going to need a not alpha and not beta.
This is where it breaks down for me, okay?
Okay?
So let's say an alpha statement is that oaks are trees, right?
You want alpha equals okay?
And that is true, right?
Sure, yeah.
And beta is trees are oaks.
Okay.
So beta is false,
Correct?
alpha is true
Okay.
by definition, right? If alpha implies beta, which it does,
Alpha implies beta.
well,
You're
I guess
saying
not.
true implies
not-
false
Not
is
in the
false.
inclusive sense. I can imagine how that could not always work, I guess is what I'm saying. Because we have to think about how it cannot work, right?
Yeah. So you try to come up with examples of scenarios in reality that disagree with this based on our intuition for how we use the word implies.
Yeah.
But once again, implies is really just defined the same way as these things. The word implies is just something we throw on there, and so you have to be careful about how someone just throws a word around implies in language versus what is meant by logic. What do we mean in logic when we say alpha implies beta? We mean exactly this. We mean true in this case, false in this case, true in this case, true in this case, by definition of implies. And we choose to call that implies. But here's the actual definition. The English word we throw in there is implies. And any time in a math textbook you see the word implies, here's exactly what it means.
Okay.
And so if a math textbook tells you that alpha implies beta, they're telling you that either this is the case, or this is the case. So they're telling you either both alpha and beta are true, or they're telling you that alpha is false. As a general rule in math textbooks, we're not very interested in vacuously true implications, so most of the time we'll actually be talking about implications in this top row. where alpha and beta are true. Anyways, so let's write these out really quick. So we have our 4 possible combinations: true and true, true and false, false and true, false and false. So if alpha is true, not alpha is false. Once again, if alpha is true, not alpha is false. And then if alpha is false, not alpha is true, right? Similar thing for beta. We have false, oops, yeah, false, oops, look at beta. False, true, true. I did that right?
Yeah.
Okay, so now let's look at alpha implies beta. So does true imply true?
Yes.
Yes. Does true imply false? No. Does false imply true? Yes. Vacuously true. And then finally, does false imply false? Yes. Again, vacuously true. Now let's look at that implication. Does false imply false?
Yes.
Yes. Does true imply false? No. Does false imply true? Yes. Does true imply true? Yes. So for any combination of propositions, whether they're both true, the first is true, the second is false, the first is false, the second is true, or they're both false, doesn't matter what combination of propositions you throw in there, these two always spit out the same value for those propositions. So they're logically equivalent. They always spit out the same value. Good? Okay. All right. So that hopefully gets us nice and comfortable with this stuff again from where we left off last class. And now we're ready to move on to predicates. Now you might remember clear back when I first told you what a proposition or what a statement was. I then read you a bunch of sentences and asked you, is this a statement, yes or no? And you said yes, no, depending on what it was. One of the ones we came across was this statement, x, I just call it statement, the sentence x plus 2 equals 5. And I asked you, is that a statement? And you naturally wanted to say yes. And I told you, no, it is not a statement. Why is it not a statement? Because it depends on what that x is. Until we put something in for that x, we cannot determine whether this thing is true or false. So it's weird things like this that have these variables in them, these stand-ins. They're asking for some value before you can evaluate it. These types of things are what we mean by a predicate. A predicate is some sort of sentence like this, such that if you gave it a variable, then it would be a proposition. If you filled in its variable. That's intuitively what a predicate is.
Are there any of those type of examples with like word problems? Like, would it just come about with like numbers, or would it?
You come across this all the time in math. X is greater than 2. That's a predicate. Five is greater than 2. That's a proposition. Well, I think good. Okay, so let's move on to the next slide. And now we're switching gears from just propositional logic to what people now call propositional and predicate logic. Or they might say propositional and first order predicate logic. What's the difference? Doesn't matter. Just know now you're doing logic with predicates. And when they say predicate logic, they mean logic when you introduce predicates in there. So you're no longer just talking about propositions. So what's a predicate? A predicate is a proposition-valued function of some number of variables, In particular, a predicate with 2 variables has a special name. What do we call it? From those of you from discrete, I don't think we have any discrete math students anymore. Oh, we stopped games in Emma. So let's get some concrete examples and then come back to that definition and hopefully it starts to click. So first off, a little bit of notation. Notation for a single valuable predicate is typically written some variable to represent the predicate p, or some name to represent the predicate p, and then the variable we're talking about x. So I might use p of x to represent something like 3 plus x equals 5. Some predicate where my only variable in there is x. If my predicate happened to have 2 variables, then I might represent it something like this. x comma y is equal to 3 plus x is equal to 5 plus y, or something like that. Some statement that has an x and y in it. And it doesn't always have to be mathematical statements. We could have done something simpler like person x loves person y. X loves y. Anything, any predicate that takes up two values or has two variables, such that if you were to fill those out, it's now a proposition. If I plug in x, this is now a proposition, and I can determine whether it's true or false depending on the value of x you plug in there. If you give me a person x and a person y, we can now evaluate whether or not this is true or false. But until then, we can't evaluate it. So anytime you see q, x comma y, with two variables like that, that's just shorthand for some predicate that needs two variables in order to determine whether or not it's true or false. Something like that means we need one variable to determine whether we're true or false. Is this making sense? Okay. Now, specifically for relations, because they come up a ton in mathematics, relations, we also have a special way of writing them. Rather than writing q, parenthesis, x comma y, end parenthesis, we also sometimes write x, q, y like that. Very common notation. So, giving you an example really quick. You're used to this relation, the less than relation being applied to 1 and 2, although you never see it written that way. You always see it written as 1 is less than 2. This and this say the exact same thing. Less than, that's just the name of our predicate, and it eats up two things. This eats up two things. Once I give it two things, it's now a proposition. So here's a concrete example. So now let's read that definition of a predicate one more time, and hopefully it makes sense. So a predicate is a proposition valued. That means when you give it the variables, a proposition comes out. It's either true or false once you give it its variables. So a predicate is a proposition valued function of some variables, one or more. And then in particular, a predicate with two variables is called a relation. Think we're good on that definition and want to see more examples?
The wording on it kind of throws me off. A proposition valued function.
Okay.
We don't know
Yeah.
if the propositions are true or false.
It just means it's spitting out a true or false.
Right. I understand it.
It's some function, p of x, so p of x, and when I plug in an x, this thing is now, the whole thing is now either true or false.
Right.
So this could be something like x greater than 4. Then p of, let's see, when we plug in 1, this is now equal to false. That is not true. 1 is not greater than 4 when we plug 1 into that proposition. P of, sorry, my chalk is, p of, terrible. Try this one more time. P of 5 is true, because 5 is greater than 4. So once you plug in something for that variable, then you can now evaluate the whole thing as either false or true. That's what we mean by proposition valued function. You can think about it as a function. You give it some input, it gives you some output. Right? You're used to working with functions. But its output is always either true or false. And never both. It's a proposition. Does that help?
Yep.
Okay. So moving on. Examples. Examples of a bunch of predicates. We could do x is blue. We could call it the is blue predicate, and we might represent it in variables like b of x, something like that. You give it the desk, it spits out false. You give it the sky, it spits out true. Y is greater than 2, we already did this one. We could call it like the greater than 2 predicate, doesn't matter what we name it. Just G, I don't know, why not? And if you give it g of x, and if you replace x with a 5, it's now true. If you replace x with a 1, it's now false. X loves y, this one's a relation, we'll call it the loves one. And you can say x, y like that, or you could write x loves y, write it like that. Either of those are possible. You plug in, I don't know, Jack in jail, it comes out true. You plug in Jim in jail, it comes out false. Whatever. This one, greater than or equal to, basically the same thing as greater than 2. I don't think we need any more on that one. Now, there's nothing wholly about one variable or two variables. Nothing special about that number of variables. We could also have 3 variables. X, Y, and Z are triplets. So the triplets one swallows up 3 people. You plug 3 people in there, it tells you whether or not they're triplets.
Is that still a relation?
Now, a relation is when there's 2 and only 2. So only in the case where it's a relation will you see this special notation that we use for relations. Like the less than, or the less than or equals. Now right here, make a point really quick. This is not a relation. That's the is greater than 2 predicate. This is the relation. Because that takes 2 variables, this only takes 1 variable. Make sense? Okay.
Why is x is greater than or equal to 2 a relation then?
So let's think about this for a second.
Is it
Oh, no,
because-
this isn't a relation. Sorry.
Okay.
If I said relation, I didn't mean to.
Yeah.
Yes.
No problem.
So just a predicate, also a predicate, but also a relation. Just a predicate, just a predicate, just a predicate. Just this is a predicate, but also a relation.
What do you mean? How about what is a predicate also?
Every relation is a predicate.
Not every predicate is a relation.
But don't you have
Uh,
2 different things affecting 2 different variables, and then just combine them?
How many variables are there in that?
There's 2.
There's 2. If I give you an x and I give you a y, can you then determine if it's true or false?
Right.
That's a relation. They do not need to be in any way related to each other. This is a pretty useless relation, but it's still a relation.
So how would you make that look in notation?
This one?
Yeah.
Pick some symbol, doesn't matter, whatever you want to call it. You can call z sub 2 if you want.
Okay.
And then it takes an x and a y. Notation is just a matter of notation. So that's just whatever floats your boat. There's just common notation that you need to be aware of. Like specifically when we're talking about a relation, we sometimes put the name in the middle. But outside of that, it's pretty much just whatever you want to call it. Okay. Note, since predicates are proposition valued, since we can give it the variables, you're just working with a proposition, we can use logical operators, meaning not, and, or, implies, and logical equivalence, or if and only if, to construct new predicates from existing predicates. I can take 2 predicates and I can and them together, in other words. So if I had the predicate x is less than 2, and I had the predicate y equals 4, I don't know, let's not say that. We'll say y is blue. Blue. I can call this predicate, I don't know what I call that, g of x, and I'll call this one b of y. I can create some new predicate now, call our new predicate n, x of y, where it is, where we define it to be equal to g of x and b of y. You can take existing predicates, and them together, and the result is a new predicate.
Which is now a relation.
And in this case, it happened to now be a relation. But that's not always the case, because this could have already been a relation.
Why do we care about labeling a relation or not?
Just because
Why is that
relations are so ubiquitous in mathematics that we like to point them out every time they come up. Because that same terminology comes up in a bunch of different fields of mathematics, and it's good to make the connection. We're always talking about the same thing. So this relation comes up in a different context in discrete math, for example, that some of these guys have taken. And it's being used the exact same way that it's being used here, although that wouldn't be obvious to them. So that's why we stress relation. Okay, so example now. So probably did something already close to it. Let p of x be the predicate greater than 2. Let q of y and z be the Love's relation. Then we can define the new and fairly useless predicate, r, which takes x, y, and z, and we define it to be p of x and q of y and z. We and those two predicates together, the consequence is a new predicate. That's all we're stressing there. You can apply the same proposition operators to predicates as well. Make sense?
Yeah.
Okay? A less useless example. Let's assume that you already know what the less than relation means on x and y when we say x is less than y. And let's also pretend that you know what the equals means on x is equal to y. Then now we can define a new useful relation called the less than or equals relation. And we define that to be less than or equals. Or to say this exact thing in symbols you're more used to, right here. What do we mean by x is less than or equal to y? We mean that x is less than y is true, or x is equal to y is true.
Now, this is not the inclusive sense of the word or.
It always is inclusive. If this is true, or they're both true.
But they can't both be true, so it's
In
not
this case, it's impossible for them to both be true.
So it's not inclusive, it's exclusive.
The
notation
or
incorrect.
is still accepting it in the inclusive sense. If I happen to put something in here where they could both be true, we would still accept the result as true. So we happen to pick a case where it's impossible to satisfy both these conditions, but that's just an accident. The or is still always being used in the inclusive sense. We just can't come up with a case that satisfies true and true.
Then that would be really, really poorly notated.
Well, we can't. No, we have to keep our notation consistent. Or that symbol always has to mean the same thing.
Yeah,
it means
of course.
if we have true and true, the whole thing's true, true and false, the whole thing's true, false and true, the whole thing's true, false and false, the whole thing's false. And just because we accidentally came up with a case where we can't satisfy both these, that means nothing.
Okay.
That's just accidental.
The or cannot be there then. It's just an accident, that's what you're saying.
No, the or can be there. If I were to plug that in a logic circuit, it would still operate the exact same way.
I don't get it.
It's just one condition that can't come up
Am I being obtuse?
in this scenario. Or doesn't care about the particular scenario you apply it to. This always functions how it functions. We use or to define something where one of the scenarios doesn't happen to come up.
So it's an empty set? What are you saying?
No, I'm just saying just because one condition doesn't happen to be satisfied doesn't change what we mean by that symbol. That symbol always means what it means,
Yeah.
regardless of context. Okay, that's all I want to make sure we
Okay.
stressed. Okay. Oops. Okay, quantifiers now. We use two quantifiers in logic and all of math. The first quantifier is called the universal quantifier, and it's that upside down A-looking symbol called the universal quantifier. And we typically read it as for all, or for each, or for every. The upside down A. We also have what we call the existential quantifier, which looks like that backwards capital E, and we typically read it as there exists. So let's read some statements really quick. Well, before we do, first we'll read the statement and then I'll point it out. So I'm going to read this statement now. This says that for all x, x is greater than 2. Make sense? This one says there exists an x such that x is greater than 2. With the existential quantifier, when you go from parentheses, you always say in English such that in between. So there exists an x such that x is greater than 2. So that's how you read it. So this one you just say for all x, x is greater than 2. This one you say there exists an x such that x is greater than 2. And that's how you read those. You with me? Now notice something here. Tell me if this statement is true or false. For all x, x is greater than 2. False. Notice how you were able to call this thing true or false though. X is greater than 2, that's just a predicate. When you apply a quantifier to a predicate, it now becomes a proposition, something you can call true or false. You couldn't call x is greater than 2 by itself true or false, but now since I add that quantifier, for all x, x is greater than 2, you can now determine if it was true or false. So when you take a quantifier and put it with a predicate, you now have a proposition. Similarly with this one, there exists an x such that x is greater than 2.
True.
True. once again, we just had a predicate, we applied a quantifier to it, and suddenly we were left with a proposition. So with a predicate, p of x, there's two ways I can turn that thing into a proposition. One is I can plug in an x. I can plug in a value for x, like 5, and then it's true or false. Another way I can make it true or false is apply a quantifier to it, like there exists an x, such that p of x, or for all x, p of x. So those are the two ways that we get from predicates to propositions. We either plug in values, or we apply quantifiers. That make sense?
Yeah.
Perfect. Stress that. Okay, bunch of examples just to get used to this language. Jump ahead using some arithmetic here, but just to help you with these quantifiers, and to help you with combinations of quantifiers now. So we're going to do for all x, for all y, I'm going to do for all x, there exists a y. We're going to do there exists an x, such that for all y. And then we're going to do there exists an x, such that there exists a y. And then the first one we're going to do is, I think I always did, I think I keep these round braces. We did x plus y equals 0. Okay, so we're going to do that exact same predicate in each of these cases. Okay, so notice we have a predicate right here. X plus y equals 0, that's a predicate. You can't tell me if it's true or false yet. It depends on what x and y are. Now, since it has two variables in it, it's going to take two quantifiers to turn it into a proposition. And then, now you'll be able to evaluate this whole thing. So let's do a bunch of examples with these to try and get you used to the language and establish some intuition for using these quantifiers. So for all x and for all y, x plus y equals 0.
False.
True or false?
False.
False. Wonderful. For all x, there exists a y such that x plus y equals 0.
True.
True. If we're talking about 3, the y is negative 3. There exists an x such that for all y, x plus y equals 0.
True.
False. There is no magic x I can find such that for any y I add to it, it always comes out 0.
Why?
What would that x be? For example, if you say 2, I say look at 5. 2 plus 5 isn't equal to 0. You're saying there exists an x such that for all y or for any y. Yes.
Yeah.
Okay. So crucial point that we just came across. These two do not
They're
say
not.
the same thing.
Yeah,
Order matters in these quantifiers. Perfect. And then finally, there exists an x and there exists a y such that x plus y equals 0.
True. Yes.
True. Okay. Help us still get comfortable with these.
The order matters.
Order matters. Correct.
Could you put like one quantifier with two variables with it?
Sometimes we get lazy. So for this one right here, we typically write for all x comma y rather than that. And for this one we get lazy and we say there exists an x and y. Because it doesn't matter if you put the y first or the x first in these, and it doesn't matter if you put the y first or the x first in these. But when they're different, order now matters, and so you can't take this, you can't be lazy like this. But this is a common shorthand that's used. Okay, so let's replace all these pluses now with times and do this exercise again, and then I think we'll be fairly comfortable with these quantifiers. So for all x and for all y, x times y equals 0.
False.
False. Wonderful. Okay, for all x, there exists a y such that x times y equals 0. True. There exists an x such that for all y, x times y equals 0.
True.
And this time it's true. What is that magic x?
0.
0. 0 is the magic x such that no matter what you multiply by, it always comes out 0. So in this case, these two happen to both be true. But that's just an accident. Okay? And then there exists an x and y such that x times y equals 0.
True.
True. Wonderful. So, think you got some good intuition for those quantifiers? Next. Okay, so now that we've gotten intuition for these quantifiers and we've used these quantifiers a little bit, now we're going to give you their actual precise definition. Okay, so let P of x be a predicate. Then, for all x, P of x is a proposition that is true if and only if P of x is true independent of x. Otherwise, it's false. Or in other words, we only call this thing true if it's always true. Otherwise, we call it false, which is what your intuition was telling you. So let's read that one more time. Then for all x, P of x is a proposition that is true if and only if P of x is true independent of x, or no matter what x is. Otherwise, we call it false. Good? Weird definition, but there you go. That's its precise definition. So with your intuition, I think the definition should now click. So let's look at an example of one of these that's true. Let's look at an example of one of these that's false. For all x, x is greater than or equal to x. It's true. Notice how x greater than or equal to x no way depends on what x is. No matter what x you plug in there, that evaluates to true. That's what we meant. On the other hand, for all x, x is greater than or equal to 2, that's a false proposition. So walk through this one more time.
I do not like this.
Walk through it one more time. Predicate is something that needs an x to be determined to be true or false. Throwing the quantifier in front of it makes it a predicate, or makes it a proposition. When is it true? When it's always true. When is it false? When it's possible for it to be false. When you can find an x that makes it false, it's false. If no matter what x you choose, it's true, then the whole thing's true.
I'm not down.
Well, do you have a specific objection?
Yeah.
Okay.
When you say for all x, then x is possibly greater than x. Now I have a big problem.
Whatever your x is, you have to plug it in everywhere the variable shows up. You don't get to choose x in one place to be a value and x in another place to be a value.
Thank
you have to
so
change
it
the symbol.
can never be greater than x,
Well,
ever.
there's an equal.
X
Oh,
can never
sorry.
be greater than x.
I might have read that wrong. Greater than or equal. Sorry. That's
Well, then we're not using or in the inclusive sense. We're using or in the exclusive sense because it's not ever greater than x. It's only equal to x.
Okay,
X is
so
only
let's
equal
write
to
this
x.
out
That's
really
a very exclusive statement, and we're using or always in the inclusive sense, and I do not like that. It doesn't make sense. Am I being obtuse?
Think about or in its inclusive sense.
I am.
Okay,
That's
perfect.
the
Stick with this
exact
table.
nature of my problem.
Stick with this table. Think about or in its inclusive sense. X is greater than x, that's always false. X equal to x, that's always true. Using the inclusive definition, this is always true. So it's always true.
That don't make no damn sense.
X is always false.
Vacuous.
Or x greater than x is always false.
Vacuously true.
It's not an implication.
Oh,
No.
sorry.
Just definition.
What do you mean?
This is a statement that's always false. Right?
Yes.
So it's false. So we have false.
Yes.
This is a statement that's always true.
Yes.
So we have false or true. False or true evaluates to true using just Boolean algebra. If you have false or true, it's true.
Be cool. Okay? Because that doesn't make any sense.
Doesn't matter what the propositions are. We'll make the first one, because this we can
Plug
also
in
call
some
this
numbers.
alpha and beta.
Plug in a number.
Okay.
Okay. Now I'm down.
Okay.
Okay.
All right.
How do we get? Whoa! We're not done.
Oh, I thought you just saw. Oh, sorry.
Thank you.
2, 2, 2, 2.
Yeah, that is not true.
You're saying this isn't true? You're saying false or true is not true.
Oh, okay.
Okay.
So in the inclusive sense, it's true because that's just a retarded way to think about it. But
In the inclusive sense, it's true, and in the exclusive sense, it's true. It's an accident that it's true in the exclusive sense.
in math, we avoid accidents, right?
I don't mean accident as in, sorry, let me think of a better word.
I'm not trying to be obtuse. I'm genuinely trying to understand this.
I mean accident as in not by design. There's tons of accidents in mathematics.
Coincidentally.
Coincidence.
Okay.
Sure. Yeah. So yes, in this specific case, we could have used the exclusive or there, but it doesn't make it false when we use the inclusive or. And every time or comes up, we mean it in the inclusive sense, and that doesn't change anything.
So help me get to where false turns into true. Just run me through that bit.
So
1 second.
or, the or operator eats up two things, just like plus. If I have 3 plus 2, by definition that spits out a 5.
Yes.
If I have true or false, by definition that spits out true.
Why?
By definition. Our or table, we had alpha, beta, alpha or beta. 4 possible combinations. It's like we're doing mathematics, but there's only 2 numbers in the universe, true and false.
Okay. It's
So we could be ORing together 2 truths, we could OR together a true and a false, we could OR together a false and a true, we could OR together a false and false. Those are all the possible combinations in our math system with only 2 numbers. If we do true or true, we call that true. If we do true or false, we call that true. If we do false or true, we call that true. If we do false or false, we call that false. So true or false is true.
We just call it that
False.
because we like it that way.
It's the definition of this symbol.
It's
This
just-
table gives the definition of the symbol.
Oh, okay. It doesn't mean it. It just it is what it is.
I don't know how else to say it.
There's no.
The table
Rhyme or
gives the
reason to
definition.
it.
So here's the thinking.
You just jammed some shit together.
Here's a possible operator. Now let's name it. Well, it looks like it operates close to how OR does in the English language. So in English they call it OR. In a math textbook, anytime you come across OR, drop the English and think of this table. This
That's
is
what it
exactly
means.
what we mean.
That's what it means.
This precisely, yes.
Okay.
It's its
All
exact
right.
definition.
Okay, I'm back to good. Sorry.
No, it's fine.
Will you write that like over there somewhere where you don't have to erase it because I'm gonna write that down. It seems important. Who got to decide this?
I don't know.
He screwed up.
Just comes up along the way.
Okay.
Did I mess up one?
No, I'm just saying the dude who decided this screwed up.
Well, we're left with history.
Yeah. Okay.
All right. So back to the quantifiers. Quantifier. This definition one more time. This is what we were talking about. So let P of x be a predicate. Then the proposition for all x, P of x, that is a proposition that's true if and only if P of x is true independent of x, or for any x you choose. Otherwise, it is false. 2 examples. Here's an example where it's true. Here's an example where it's false. The important thing to notice is the quantifier turned it into a predicate. Well, actually, it's also important to notice when it's true and when it's false. Feel like we're good with the definition?
We're trying.
It turned into a
Right.
predicate or a proposition.
Yes, this is now a proposition.
Okay.
This is now a proposition. Okay. Let P of x be some predicate. Now we're going to come up with a definition based off of this definition. We're going to define our existential quantifier now. And in mathematics, we never define a new symbol on its own if we can define it in terms of its old symbol. And so it just so happens that we can define the there exists one in terms of this one. And so that's how we're going to define it. Rather than coming up with a new definition like this one, which just works. So we always try to reuse our definitions to the best of our ability in defining new terms. So it's going to seem a little bit awkward, but once we go through some examples, I think it will make sense to you. So our definition, let's just read it. Let P of x be a predicate. Then we define the proposition, there exists an x such that, P of x, we define that to be, it is not the case that for all x, not P of x. Very ugly definition, it seems, right? So let's say some sentences in English and then come back to that definition. Well, let's do them both at the same time. So there exists an x such that some predicate of x, let's think about a concrete example. Here's a concrete example of a sentence. There exists a swan, that's our x. There exists a swan such that it is black. So this is the x is black predicate. So there exists a swan such that it is black. Sorry, I say such that so much. I'm going to do s dot t left and right. So that's one of those things you just got to get used to. There exists a swan such that it is black. Now notice that that says the exact same thing as it is not the case. That's often how we write that not. It is not the case that for all x, or for every x, in this case we're talking about swans, for every swan, it is not black.
So this addresses my, oaks are trees, but not all trees are oaks objection earlier, right?
Not really. This is showing you how to go back and forth between quantifiers.
Okay.
We're seeing how to take a statement that has a there exists and turn it into a statement that says for all or for each.
So are the x's that are in the quantifier and the
In this case, x is going to be a particular is swan.
is swan?
Uh-huh.
But it's also black in next to the p.
No, the it here references a swan. So the predicate P, so let's write some things down. The x that we're talking about is swans. The P that we're talking about is black predicate.
Oh, okay.
So it should have said x is black, sorry. It's the x is black predicate. So there exists a swan such that it is black, is this thing right here. That's the same thing as it is not the case that for every swan, it is not black. If it is not the case that for every swan, it is not black, that means that there has to be some swan that is black. Those encode the exact same information. There exists a swan such that it is black, or there exists a black swan, says the exact same thing as it is not the case that for every swan, it is not black.
Yeah, that's obvious. We're down.
Everyone good?
Yeah.
Okay. In general, here's how we think about it. There exists an x such that some predicate about x says the exact same thing as it is not the case that for every x, not that predicate about x. That's it in English. So probably did these in backwards order. But hopefully now when this one clicks in English, you can come back and look at the definition and make it all sit. The there exists is right there. There exists an x is right there. Such that P of x is right there. Similarly, it is not the case. Is that not right there? That for every x is right there. Not P of x, not P of x.
And we need that all in case, all intact, to say, let P of x be a predicate.
We need to understand this because by definition, when this symbol comes up, by definition, it's a shorthand for this. So first we define this symbol up here. So now I have this thing defined. And now I need to define this new thing. I define the new things in terms of the thing I already have defined, like that. Okay, we'll get into some examples using these and do a little bit of proofs to help make it comfortable. Oh, if I'm going to do that proof, I'm going to need to write that definition. So, sorry, should have wrote this on the next slide too, so you can see it.
You got
We'll
a
write up
typo
here.
on that slide, don't you?
I'm sure I have a lot of them.
Bulk is not bulk. Instead of black.
Ah. So, there exists an x such that P of x, we're saying by definition, this is not for all x, not P of x.
So the colon and the equal sign means by definition.
So the equal sign means they're saying the exact same thing. The colon there means I'm defining the thing on the left in terms of the thing on the right. So whatever side the colon shows up on, that's the thing that we're defining now. So common notation in the book. If you're using equals, it's like that. If you're saying they're logically equivalent, it's going to be a colon and then back and forth arrow. That's more rare. Typically, you see it like this because back and forth arrow only makes sense in logic. But I don't know. I assume math textbooks still use that symbol a lot. But in case you didn't know
But
about that,
then the
there
order
it is.
of
The order
matters.
matters. This is the new term. These are your existing terms. Okay. So we got that up there. Let's now do some proofs. And
I'd like to really have some words with the guy who came up with that other definition because it's not.
Okay. So going to do our first proof now. You know, I'm probably going to need some of the whiteboard space. So let me also do what I'm proving. So this was a definition. Now what I'm going to prove is that for all x, p of x is logically equivalent to, it is not the case that there exists an x such that not p of x. Okay, that's what we're going to prove. So get rid of this so that's not in your way and in my way. And let's know what we're trying to prove here. So we said by definition.
When you use the double arrow, that's the same as saying an equivalence.
Yep, logically equivalent. I should have put equals here. I really should have done this. By definition, this is logically equivalent to this. Okay, so now let's notice what I'm trying to prove and see how it relates to the definition we already have. We said by definition there exists x such that p of x is this thing. Now notice I'm just switching the quantifier. I'm going to show then for all of x, p of x is logically equivalent to not there exists an x, not p of x. So swap the quantifiers and the statement's still logically equivalent, in other words. And I'm going to prove that real quick. You with me? So, proof of that thing over there. So, chalk has run its course. So, 1, let p of x be some predicate. We know nothing about p of x except that it is a predicate. That's all we know about it. 2, define q of x. So I'm defining a new predicate, and I'm going to define it to be not p of x. We already talked about how, since these things are propositional valued, I can apply logical operators to them, and it's still a predicate. If p of x is a predicate, not p of x is still a predicate. So we still have a predicate. You with me? Now, 3, by definition, we'll call it definition 1 up there. 1, comma, there exists an x such that q of x is logically equivalent to not for all x, not q of x. So I'm just applying this definition with the predicate q of x. That's all I have written here. You with me? Okay. So then,
Q not to be understood in the sense of a relation.
Q is not a relation, just a predicate. Okay, so now, 4, then, by definition of Q of x, there exists, oh, did I skip a step? Sugar, I shouldn't have plugged that in yet.
So when you used Q to notate a relation earlier, is that a common notation?
P and Q are common ones.
Coincidence. But it's not a rigid thing.
It's not a rigid thing, no. Names of things are completely up in the air. Okay, so then, sorry.
Except when they're not, like this other table over here.
Right, unless it's a well-defined operator. We just mean the names of things. Here, naming that. Anyways, so now, what I was trying to prove is what for all x p of x equal. Sorry. So then for all x p of x, I'm trying to show that this is logically equivalent to this thing. Now, I know that this is logically equivalent to, replace p of x with q of x. Not q of x. Then apply my definition. Now I want to do the definition first. Let's do the definition first, sorry. And then we'll replace it. So by definition, for all x p of x.
So do you need your little colon for the notation?
No, I'm still weird. Let me think. For all x p of x, so I'm trying to prove, for all x p of x, let's see, do I want a not here? Let's see. Then not for all x p of x is logically equivalent to not for all x, not q of x. If I replace my p of x with a q of x.
So in step number 2, Donnie, to notate that property, do you want your little colon?
It's not a definition in the sense of we're going to be using this from here on out in mathematics. So maybe I should have done a let.
Okay.
So we reserve that for, this is a book definition that you'll reference for every problem from here on
That's
out.
just.
This is just a quick let for getting me through my proof. Okay, so for not all x p of x is the same thing as not for all x p of x, because remember, I just let q of x be the not of p of x. So now, by our definition, not for all x, not q of x, is this same thing. You with me?
No.
Okay. Started out with not for all x p of x.
Okay.
Now that's logically equivalent to not for all x not q of x, because q of x is not p of x. So replace p of x with not q of x. Okay? And then from this definition, if I have not for all x not some predicate, then that's the same thing as there exists predicate. So this is logically equivalent to there exists and then that predicate. Good? Plugging now back in the p of x into there, this is logically equivalent to there exists an x such that not p of x, and then I wasn't smart in the beginning. Rather than putting a not here, I should have defined this to be double knots.
Well, it doesn't have to be elegant, does it?
No, it doesn't have to be, but it would be easier for you guys if I would come with a better proof in mind than making you suffer through this.
If it's inelegant, do you get teased by other mathematicians?
I don't know a lot of other mathematicians, and I'm technically not a mathematician. I don't do it professionally. But, there we go. So, skipped one step that I probably should have done before this. So, for all x, p of x is the same thing as, let's squish it in up here, is the same thing as not for all x, p of x, and I think we're good from here.
Okay, the not throws me off.
Not, okay, should have done a truth table for that real quick. If I have alpha, this is not alpha, this is not alpha. If alpha is true, not alpha is false, not alpha is true. If alpha is false, not alpha is true, not alpha is false, so not alpha is logically equivalent to alpha.
So what's the point in not alpha?
Yeah.
Just to help you work out a definition. So take this one step at a time now, the way I should have said it to begin with. So for all x, p of x is logically equivalent to not for all x, p of x. Agreed? Now I'm going to replace that p of x with a not q of x. That's a bracket. This is a bracket. That's still a not symbol. And that's still a not symbol. So we still have both our not symbols. Going from this line to this line, all I did was replace p of x with not q of x and add some brackets to help us see how we use the definition. Go ahead.
Because you would like distribute that not through the other brackets, is that what you're saying?
So,
I don't get the not thing, it seems like.
all right. Let's redo it now that I know exactly what I'm doing
Okay.
and clarify everything as we go. Okay. So, for all x, p of x is logically equivalent to not, we'll put square bracket there, and then the parentheses here, for all x, p of x.
Yeah, I just don't know why you'd put yourself through all that.
So I can use my definition. So now, the next line going from here to here, all I'm going to do is replace p of x with not q of x. So this is logically equivalent to not for all x, not q of x. Right?
Johnny,
Go ahead.
I'm confused where you're getting your not q of x because you don't have it in your definition.
I see what you're saying. If q of x is not p of x, then that's the same thing as p of x
Oh.
is not q of x.
Okay.
Okay, good point. So if we define q of x to be not p of x, then p of x is not q of x.
Right.
Okay, so that's a substitution. So from here to here, all I did was replace p of x with not q of x. Good?
Yes.
Now I'm applying this definition right here. If we have a not for all x, not some predicate, not for all x, not some predicate, we can replace it with there exists x, that predicate. So I can now rewrite this as not, and everything inside square brackets gets replaced with there exists x, such that that predicate. That's what the definition says we can do.
Now, will you explain when you negate a quantifier, does it reverse that quantifier?
That will be the next two theorems we do after this one.
Okay.
So I know what you're talking about. Yeah, we'll get there. So, but you're good with just here to here, we're just using this definition.
What's the
Okay.
the culture here, because this seems kind of obtuse, is this because we unnecessarily nitpicky? What's the culture?
Unnecessarily nitpicky.
I mean, it's kind of obvious.
Mathematics is proofs, and so almost every problem that we do in the class is going to be proofs. And so I'm actually being kind of fast and loose rather than nitpicky.
Really?
Yes.
Okay. So this is the fast and loose version.
This is the very fast and very loose version.
Okay.
Okay. So from here to here, we just use this definition, right?
Mm-hmm.
And now, I'm going to substitute out my q of x with not p of x. And then we don't need these square brackets on the outside anymore. They just no longer serve a purpose. So we have not, there exists x, such that not p of x.
So you just distribute it.
Didn't distribute it. We'll talk about distributing and not across it in a second. That will be what we do with our next two theorems.
So when do we decide we have to prove something? Because I'd like that other thing proved.
That's a definition.
Yeah,
You
can
don't
we
define
just-
defin-
does
or you don't
somebody-
prove definitions.
When do we get to decide to define shit versus prove it?
You can add any definitions in mathematics as you go to your heart's content. We just define this to be shorthand for this. We just define that symbol to be shorthand for this table.
Let me do that if we want to.
Yep, you can throw in any definition you want. Now there's sharing definitions that everyone uses, so if you don't use those same definitions, people get confused. But yes.
Me.
Well, I mean the community who grows up using those symbols.
Okay.
Anyways, so notice now what did we prove? I proved that for all x, p of x is logically equivalent to not there exists x, not p of x. So in other words, here was this definition. We showed that swapping those quantifiers still produces a true statement. That's what we just proved. Does that make sense?
Yes.
Okay, so now we're going to do two more theorems using these really quick, and it will be easy now that we have these two. So one, we want to prove that not for all x, p of x, where p of x is some predicate, is logically equivalent to there exists an x such that not p of x. You with me? Okay. One, let p of x be some proposition, be some predicate, I mean. Okay, two, by theorem, we'll call it theorem one. So this right here is theorem one. This is something we proved. This was a definition, this was a theorem. This was something we proved. So by theorem one, we know that, oh, are we going to use the theorem or the definition? Theorem. Okay. We know that for all x, p of x is logically equivalent to not there exists x, oops, there exists x, not p of x. So now I'm going to not both sides. So then, not for all x, p of x is logically equivalent to not there exists an x such that not p of x.
Will you help me understand why that's important?
Because now we have, finally, this is logically equivalent to, not is the same thing as just our proposition. Remember, this right here is just a proposition. So not a proposition is the same thing as just a proposition. So it's the same thing as there exists x such that not p of x. And so we just really showed that this is logically equivalent with this, which is what we were after. So the way that we say that in words is when you distribute a not across the for all quantifier, it turns it into an existential quantifier. So if I take the not on the inside, it switches my universal quantifier into an existential quantifier. And now we're going to show the exact inverse of that. We're going to show not there exists x, p of x, is the same thing as for all x, not p of x. Let p of x be a predicate. Then by our definition now, this thing, we know that there exists p of x is logically equivalent to not for all x, not p of x. Then we apply the not to both sides. So we take this same thing and apply a not to it. We need to take this same thing, and apply a not to it. The not and the not cancel out, leaving us with just for all x, p of x. So when you distribute a not across an existential quantifier, it turns it into a universal quantifier. Make sense? That's the value there. And so, now with those notions in mind, let's go back to negating some statements that we did at the start. And some of you might have been a little bit surprised how people could negate the statement so fast. And they were using exactly what I just talked about. So what I just proved for us, two little things, oh, we have them written right here. So here's the two useful ones when we're thinking about how to negate a statement. So let's go back to statements we took the negation of, and now we're going to negate them again, keeping these things in mind. So go back to our statement, all men in Georgia are at least 6 feet tall. What's the negation of that statement?
Some men in Georgia.
So if we want notice that this is, first off, let's think about the form of this statement. All men in Georgia are at least 6 feet tall. This has the form of, for all x, some predicate of x. It has this form, right? So if we want to negate this, negate this is the same thing as this. So if we negate this, we're left with, there exists x, not p of x. So I take all men in Georgia are at least 6 feet tall. If I want the negation of that, we say there exists someone in Georgia who is not at least 6 feet tall, or is less than 6 feet tall, or 6 foot or less. Oh no, less than 6 feet tall. However you want to say it. So before, you guys might remember as you were trying to wrap your brains coming up with how exactly do you negate these statements, and other people in the class, they were just spitting it out. They were keeping these facts in mind. And that's how they were doing it so fast. So all students in France like geometry. There exists a student in France who doesn't like geometry. Every rectangle is a square. The negation of that is there exists a rectangle that is not a square. You see that? And that's a shortcut that they were using when we were doing all those statements and why they did it so fast. Okay. So, moving on now to talk about proofs.
We go
ahead.
back to that last slide.
Sure.
We do the example of every circle has a center. How do you negate that?
For every circle, it has a center, so it's of this form. So the negation of it is there is a circle who doesn't have a center.
But there isn't.
And we're not saying that it's true. We're saying it's the negation of that proposition. If this were the proposition alpha, sorry, which one are we on?
Every circle.
This one. If this were the negation alpha, or if this were the proposition alpha, then what would the proposition not alpha be?
They're just a circle with a center.
Without a center.
Oh, right.
Right. That's all we're saying. We're talking about how to negate a proposition.
Doesn't matter whether it's true or false.
Yeah, it doesn't matter whether it's true or false. All that matters is that it is something that's true or false. Okay. So now, proofs. In mathematics, all you do over and over again with everything you do is proofs. Every field of mathematics is simply determining the logical implication of the given field's axioms. If you're talking about geometry, what do? You start out with the postulates. Those are the axioms, postulates, same thing. And then you apply logic to them to determine their logical implications. That's it. That's all you do. In algebra, same thing. Topology, same thing. Any field of math, this is exactly what you do. It's all math is. And then we just create definitions along the way because definitions are nice for saying a lot of things in a few words. That's what definitions do. And so any textbook you open up in mathematics is going to list out your axioms, and then from there on out, just list out definitions of theorems. They have a few different names for theorems. Sometimes they'll call it a, what do they call it? A lemma. Sometimes they call it a corollary. Same thing. It's just a logical implication. So there's just theorems, definitions, and axioms. And undefined terms for those of you who have gone deeper into axiomatic systems. If you don't know what we mean by that, that's fine. But to be complete, there are those. Okay. The crux being, or the point being, that proofs are essential to doing mathematics, understanding how to do proofs.
Will you help me understand the difference between theorems, definitions, and axioms?
So an axiom is some assumption. So one of Euclid's axioms is 2 points, define a line.
So it's how is that different than a definition? Because we can just make anything we want a definition.
We didn't define a new word here. He assumes you now know what all those words mean. An axiom tells you a relationship between words. If you have 2 points, well, that gives you a line segment is what he meant, but that's the terminology he uses. So an axiom, here's another way to think about it. An axiom can always be stated in terms of if-then. No, that's still not true. That's only if it's associating things together. But your axioms are base assumptions. You start out with your axioms before you even have definitions.
Okay.
So axioms are base assumptions, and then definitions are things that you could remove from mathematics and everything is still the same. You never have to use a definition in mathematics. We need axioms because that's our starting point. We start out with some axioms, and we say these two axioms together imply some conclusion, and we wrap that together in a theorem. We say these two together imply some theorem, or imply some conclusion, and we wrap that together in a theorem. And we might say, and then this conclusion, along with that assumption, together gives us something new. So you start building out this web of implications from just your axioms. You only start with your axioms. Definitions you never have to use. We use definitions in mathematics when in our theorems, we come up with some abstraction that seems useful, that we're going to reference a lot, and so then we just throw in a definition real quick and go on our merry way. But you never have to use definitions. You have to have axioms, have to have theorems.
Axioms are important. They're the base.
They're your base assumptions.
They create theorems.
You look at their logical implications, we call those theorems.
Okay.
Okay, so all proofs are just demonstrating that given some set of assumptions, some conclusion follows. What we do over and over again. Common proof styles, easily verified with alpha implies beta, so let me write that table out really quick. And then show some common things that we do in proofs, but you'll see tons of examples of proofs. So let's try it out really quick. We have alpha, we have beta, we have alpha implies beta. So, one more. We can have true, 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 false, false, true, false, false. True implies true is true, true implies false is false, false implies true is true, false implies false is true. Okay, so two common things we do in mathematics.
We run the whole false implies true thing through with me one more time.
So this is where it's vacuously true.
So this is where it's vacuously true. If the antecedent for an implication can never be satisfied, we call the whole implication vacuously true.
That is messed up.
Use your purple dragon.
Use words. What do you mean?
So, common example, I say, if Donnie's a purple dragon, then the sun's made out of marshmallows. That is a true statement.
The hell it is.
The antecedent's false, the conclusion's false, but the implication is true. If I'm a purple dragon, then the sun's made of marshmallows. It's vacuously true, because the antecedent cannot be satisfied, because I am not a purple dragon. It's a definition of vacuously
It's
true.
very pointless in mathematics. Vacuously true statements.
We hardly ever deal with them.
Hardly ever deal with them means I can just disregard it for the rest of my life.
Unless Donnie's a purple dragon.
That's your choice.
Well,
Vacuously true. I mean, it does come up,
it
but
seems really obtuse and backward.
okay,
Is it?
no.
So I'm obtuse and backward.
Well, you can't expect every time you come into contact with a new concept that you just instantly love it and it just takes hold. Things take time.
If something is false, that implies that it's true.
No. If you have a false antecedent and a false conclusion, the implication is true. If the antecedent's always false, the implication's always true. We're calling the implication true, which we're calling this thing true. We never said beta is true. We're saying if alpha is false, then the statement alpha implies beta is what's true.
That's
It is
the
very
dumbest
weird.
thing I've ever heard in my entire life.
That's a wonderful life.
Really?
I think so.
Sitting here, I just encountered the stupidest thing I've ever heard in my entire life.
If you don't like the language,
Well, I don't
then
get
think
it.
about it as just a definition. Here's the definition of that arrow. What does that arrow mean? It means this.
Okay, we're back to that. Okay, so I just need to talk to the dude who decided that.
To call
dumb
that
shit.
word implies, to
Yeah.
put the English word implies there?
Okay,
Sure.
I'm down. It's defined.
Yes. It's just a definition. It's not something we prove. It's just a definition.
Yeah, if I ever came up with that was on crack.
Oh, we were going to use that for this. So again. All right, alpha, beta, alpha implies beta. true, 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 false, false, true, false, false. True implies true is true, true implies false is false, false implies true is true, false implies false is true. So now, common ways we prove things in mathematics. Two things we show. If you know that alpha is true, and you know that alpha implies beta is true, then what do you know? So let's come look at this table. Let's assume that we know alpha is true. So now we're talking about one of these two cases, right? Ignore the bottom two. And if we know that alpha implies beta is true, so now I know that we're in this row or this row. So I know we're in this row or this row, and I know we're in this row or this row, then I have to be in the top row. And therefore we know that beta has to be true.
Okay.
So if alpha is true and alpha implies beta is true, then beta has to be true.
Okay, I stopped running because of the bad one. You run that one more time.
The bad one.
Can you leave the bad one out? The third one down?
This one?
Yeah.
No, I can't leave anything out. It's its definition.
What about the bottom?
So we knew because alpha is true that we're talking about one of these two rows. We knew since alpha implies beta is true, we're talking about one of these two rows.
But the bottom one, it can't be
bottom's
the third
true
row.
too.
Oh, sorry. Thank you. Is that what you guys were saying? Sorry, my bad. Good catch. Wonderful catch. So since we know that this is true, we have to be talking about one of these three cases. Since we know that this one's true, we have to be talking about one of these two cases. With both of them true, we have to be talking about the top case. And so what can we conclude? That beta then has to be true. So if we know that alpha is true, and we know that alpha implies beta is true, then we know that beta is true. Make sense? So oftentimes we prove some general theorem, alpha implies beta, and then we give you some assumption, alpha, and your job is to then combine these two to see what they imply, beta. Common set for a problem you have to solve.
So we have to memorize this table.
Yes, you have to know that table very, very well to do proofs.
So could you give an example of that, like a story example?
Give you an example of what we just said.
Yeah. Alpha is true and alpha and beta are true.
Sure. We might prove that 2 plus 3 is equal to 5. Or maybe it's given to you. We'll do a bunch of exercises with this right after. So we have a bunch of exercises right around the corner. Okay, another common proof strategy. Well, I think we still follow. I'll just put my arrows here. Another common proof strategy. If you know not beta, so you know beta is false. Where is beta false? We're talking about this row and this row. Good so far?
Yep.
And you know that alpha implies beta, which means we have to be talking about this row, and this row. Then what do you know?
That alpha and beta are false.
Right, but we already knew beta was false. And then we also knew that alpha implied beta. So our conclusion is that alpha then is false. So that's another common proof strategy. If you know not beta, and you know alpha implies beta, then you know not alpha. A more crystal clear way of seeing that without this truth table, you might remember what's the contrapositive of alpha implies beta? It's not beta implies not alpha. That and that say the exact same thing. So if you know not beta, and you know not beta implies not alpha, then you know not alpha. So whichever of those appeal to your intuition better. I personally like to think about it this way, but books come up with their examples for reasons. So good? Wonderful. So now we'll get to an example, and a nice wordy example for you. So you know that if it rains on commencement day, then the graduation ceremony will be held in the gym. So you know alpha implies beta. If it rains on commencement day, then the graduation will be held in the gym. Alpha implies beta. Now you also know that today is commencement day and it's raining. Or in other words, you know that alpha is true. What can you conclude?
Beta is true.
Beta is true. Therefore, since both alpha implies beta and alpha are true, we know that beta, in other words, the graduation ceremony will be held in the gym, is true. So there's a wordy example of the first style of proof. The one where if you knew alpha, and you knew alpha implies beta, then you know beta. Next we're going to do, if you know not beta, and you know alpha implies beta, then you know not alpha, and this one's going to be of that type.
This one's gonna be which?
Of this type.
Oh,
So this one was of this type, now this one's going to be of this type. Just to give you a taste of two common proof styles. But there's tons of ways to prove these. Okay, so Jim claims that -3 is a root of x squared minus x minus 6 equal to 0. What does that mean? If it's a root of this, it means if you plug -3 in for x, you'll get 0. So Jim, he's some guy, he claims that -3, when you plug in for x, makes that equation true. Okay. Now, if -3 is a root of that expression, then plug it in, -3 squared minus -3 minus 6, so we just replaced all our x's with -3's, right? Has to equal 0. That would be alpha implies beta. However, -3 squared minus -3 minus 6, what is that? We have 9 minus -3 is the same as plus 3. So we have 9 plus 3 is 12, minus 6 is 6. It's not 0. So our conclusion is false. Beta is false. Therefore, since alpha implies beta and not beta are true, then we know alpha is false. Or in other words, Jim is wrong. Jim claimed that -3 is a root of that. So this is our alpha. -3 is a root of that, that's our alpha. We know that if -3 is a root of that, if alpha, here's our alpha again, alpha, alpha. We know that if alpha, then this follows. That's what it means by definition to be a root. Then beta. But here we know not beta. Here we know not beta. Therefore, we know not alpha, saying that alpha, -6, oh.
not beta is true.
Therefore, we know not alpha is true.
Or not beta is true.
The not of the thing. So Jim's wrong, in other words. We just proved Jim wrong. Alright? Jim claimed alpha, we just better show, no, alpha is not true. Common proof styles.
Can we do that with the vacuous thing?
Neither of these use vacuously true.
What do you mean by that?
That's because they're.
We said assume this is true and this is true. The case we had wasn't a vacuously true case. I mean, I guess you could think about this one was using a vacuously true case. That one was using this case right here. Because I have false implies false, but we also think that about that as not beta implies not alpha. Because false implies false gives you the exact same thing as true implies true. If you switch it like that.
Is the vacuously true thing ever useful in real life?
Well, we just rarely use this case.
No, that's not vacuously true.
Oh, this case right here?
Vacuous, that's the bad one.
Oh, so that's what you mean by the bad one. Okay.
I want to do one with the
It's
bad one.
rare. I don't have one off the top of my head, so
Okay.
I don't know if it does. Okay.
That's the black sheep of the logic thing.
All right. Now, basic law of logic, one more thing we need to add on to us, this before we're ready to go. Don't worry, it's just this one slide. So we did propositional logic, then we added predicates to it, so that's called propositional and predicate logic. And now we're going to add what we call the law of identity to it. We've been using equals up until now. Now we're going to define exactly what we mean by equals. So technically, the logic we're talking about now is called propositional and predicate logic with identity. Just to give you the technical name, which is the logic you use to construct mathematics. So this is the last piece of logic we'll go over. Identity. So law of identity, it can briefly be stated as everything is identical with itself. It's often stated as A is A or A equals A. If you come across it in a logic textbook, here's going to be its definition. For all x, x is equal to x. Everything's identical with itself. Law of logic. Basic assumption. not something we prove. Okay, so now we're going to do a couple proofs that are proofs of logic. These are not mathematical proofs. These are proofs of logic. What do we mean by that? We mean that these proofs are going to be true in algebra, in geometry, in physics, in biology, in music theory. These are consequences of logic. They have nothing specific to do with mathematics. And so, when we list out our axioms for mathematics, you're going to notice that this one isn't on there, but I'm going to use it left and right. It's because it's not an axiom. It's a theorem of logic. It's more basic than an axiom. It's not specific to one field of knowledge. The way that 2 points define a line segment, that's specific to Euclidean geometry. We don't use that in arithmetic. This is used everywhere. Fundamentally different from an axiom. It's a theorem of logic. Okay, so this is what we're out to prove. First we're going to prove 2 simple cases, and then come back to this one and prove it in general. The law of identity. We're going to do a proof if A is equal to B, then we'll erase this, or we'll close this and give us some space. If A is equal, not alpha, if A is equal to B, then A plus C is equal to B plus C. So let's start with this proof really quick. So if then. Common way that you start by proving an if-then statement is you start with let, and then you write your antecedent. Our antecedent is A equals B, so let A equal B. 2. Maybe we say something like observe that A plus C is equal to A plus C, using the law of identity, right? Then, since A equals B, we get A plus C is equal to B plus C. Substituting out that A, or substituting out that A with a B.
So you'd have to write all that down instead of just subtracting C from each side.
We have no notion of subtraction. These are so far just symbols on a paper. I start with plus to make it appeal to your intuition, and then we'll move to the more abstract. Good? So we're going to use this exact same logic, but now I'm going to replace that plus with a circle. And we need to say, we're going to have to throw on something else. If A circle B, if A circle C and B circle C are defined, in other words, they mean something, comma, and if A is equal to B, then, lowercase t, then A circle C is equal to B circle C.
What is the circle
Anything.
notating?
Any random symbol you want, as long as it's defined in this case and it's defined in this case, you're fine to use it. So as long as A circle C is meaningful and B circle C is meaningful, and if A and B are identical, then you're guaranteed that A circle C is identical with B circle C. That's what it's saying. And the proof for this goes the exact same style. 1, let A, B, and C such that A circle C and B circle C are defined. And let A equal B. 2. Then we know that A circle C is equal to A circle C using identity. And then we know, since A is equal to B, this is the exact same thing as B circle C is equal to A circle C. And we're done. And this is true for no matter what that circle thing is. So now you can plug that in with plus, subtraction, multiplication, division, the ones you're used to. But this goes beyond just those basic operations. This says in logic you can and the same thing to both sides, or you can or the same things to both sides, or you can not the same thing to both sides. This is what gives you your rule in algebra, that you can do whatever you want as long as you do it to both sides of the expression. Now, important note, A circle C and B circle C have to be defined. What's the big exception in algebra? You can do everything to both, as long as you do the same thing to both sides of the expression, you can do anything except for what? What's the big exception? Huh?
You have to do it to the other.
Well, what you do to one side, you can have to do to the other. If x equals y, what I do to one side of the equation, I have to do to the other.
Divide by 0.
Divide by 0. That's the one thing we can't do to both sides. I can't take x and divide by 0 and say that's equal to y divided by 0. Why not? Because a divided by 0 is not defined. So this does not say that you can divide both sides by 0. But outside of that, we just proved for multiplication, division, and any other operation you can think of.
You don't even have to say that because it says as long as it's defined.
Right.
Divided by 0 is undefined by definition, right?
Division by 0 is undefined.
Yeah.
That is correct. So yeah, in that exact case, if we plugged in the symbol division here, that would look like a divided by 0, which is undefined.
Is that a weakness in our number system? Or is
Uh,
it just because the guys who came up with definitions decided to avoid that problem?
It's if you define 0 to be equal to anything, you can define it to be equal to everything. If I make a divided by 0 equal to anything, I can make it equal to everything. And then it's no longer defined because I can't define a number to be every number.
Well,
So the
that
rules of our
problem-
systems
that
makes that if
problem
you
is-
try to define it to be anything, then you can make it equal using our rules, our axioms, you can make it equal everything.
Well, if I take a pie and divide, can we digress for a minute?
Sure.
Because the whole not dividing by 0 thing bothers me. So if I take a pie and divide it by 0, my boys say, thanks, Bob, we'll eat it. It's pie. I didn't take anything away from them, and they eat it. It exists.
Divide isn't takeaway. Divide is to break it. I mean, if you want the physical intuition for what divide is, you take your pie and you break it up into pieces of 0 size. How many pieces do you have?
0.
Do you have 0 or do you have infinite?
You have infinite. You have an infinite.
No.
You have an infinite number of slices of
That
pie
is
because
the
there's
most-
an infinite number of points between any 2 points.
Well-
You can slice that pie an infinite number of times.
You can slice a
But
pie
it's
into
not
infinite
any
times.
pieces.
Shut
And
up.
so in
that
mathematical
most
notation, we say the
respectful.
limit as x approaches. Which way do we want to do it? Well,
No, I'm close to understanding this, so carry on.
we will prove in this class that you cannot divide by 0, and we will show the exact
Can we
problem.
do it right now?
No, because we don't have our foundations. Okay, so our important rule of logic now. We got the one rule of logic that we use in math, left, right, all over the place. It's what you do to one side, you can do to the other side, as long as what you're doing is defined. Division by 0 is not defined, so you can't do that. Multiplication by 0 is defined, so you can do that. Good?
Who got to decide that?
It's a consequence of our axioms. It's not a decision somebody made. It's if we use these axioms, then this is a consequence of them. I don't know how else to say it. We'll prove it.
Awesome.
Okay.
That's why I'm here, by the way.
No, that's fine. It's what we're all here for.
Yeah.
Okay. I don't know. We can jump into a couple of these, and then we'll be done for today. And we'll come back and finish up these as a refresher for next time. And just so you see where this is going, we'll go through some exercises, and then we'll get into the axioms that we use in algebra, which are these things right here.
Sweet.
Well, here's some of them. There's 3 that aren't listed. So just to give you a heads up of where we're going. Anyways, so let's now use some of the tools we've been talking about to prove a couple of these things. So we have, I'm going to call it axiom 0, but it's not a 0. It's not an axiom. This is what we just proved. I'm going to write two special cases of what we just proved. We just barely proved that A equal to B implies A plus C is equal to B plus C. And we just barely proved that A equal to B implies A times C is equal to B times C. A equal to B and C not equal to 0. Implies A times C equals B times C. So this is what we got from logic. And now I'm going to give you two axioms, and we're going to do some basic proofs, just to get a feel for for proofs.
Okay.
Make sense? Okay, so prove. Prove if x is equal to 5, then 3x plus 4 is equal to 19. So that's what I'm going to do a proof of really quick. Proof of 1. So 1, when we do a proof, we start out with let our antecedent. You don't have to, but just common proof practice for people first learning how to prove. Let x equal 5. 2. Then 3x plus 4, we need to show that that's ultimately equal to 19. So then 3x plus 4.
Skip, you went down a problem. You went
Oh, thank you.
Instead of we're still going over.
Then, I said the right thing.
Yeah.
Then 3x plus 4 is equal to, we'll shut this while we do it and then flip that back. Then 3x plus 4 is equal to 3x plus 4 is equal to 15 plus 4 is equal to 19. Nice and easy. Type of proof you've been doing all through algebra, although you probably didn't call it a proof.
You keep doing that square thing that you.
Oh, sorry. So this little square thing is a symbol that you put at the end of your proofs. You used to put QED, and it used to be some Latin phrase for thus it is demonstrated, and now, so this was shorthand for a Latin phrase that meant thus it is demonstrated, this is shorthand for that. And so it's something you put at the end of the proof, makes it clear to the reader, my proof's over, we're done. The thing guys after should now be demonstrated. Good?
Yeah.
Thanks. Okay, next one. I kind of need those to be up so we know what we're referencing. Just gonna have to leave this open now and write over it. We'll write it. No, I'll just have to write smaller. Sure.
You could just
Dude, maybe I can skeet the projector. Yeah, get that. It's, make that all ski wampus, but worth having the space. Okay, so now I'm going to prove the inverse. And this one's going to be a little bit more interesting. So I'm going to prove that 3x plus 4 equal to 19 implies x is equal to 5. Or if 3x plus 4 is equal to 19, then x is equal to 5. So 1, we start out with let our antecedent. Let 3x plus 4 equal 19, right? Now, how do we continue from here? Divide.
Or sorry, minus.
Minus. How do I know I can minus?
You can subtract 4 from each side.
So I can rewrite this as 3x plus 4 is equal to, I can rewrite 15 plus 4, right? That's the same thing as 19, right?
Oh, okay.
Okay, now, using axiom 1, now using A1 here, I can now take this and write this as 3x is equal to 15. Axiom 1 says for all integers a, b, and c, we're assuming that these are integers, if a plus b is equal to a plus c, then b is equal to c. So I actually should have changed the order I wrote this. If I can write 19 as 4 plus 15, and I should rewrite this as 4 plus 3x. So let's reread that. If a plus b is equal to a plus c, b is equal to c. So if I have the same thing here on both of them, and some other expression here, those other expressions have to be equal. That's using axiom 2. Now, I can rewrite this as 3x is equal to 3 times 5. Sorry, 5, right? And now, using axiom 2, using axiom 2 right here, I now know that x is equal to 5. Because axiom 2 said if you have the same thing multiplied by some terms, those terms are equal. And we're done. So that one's a bit more interesting. Make sense? Okay. We can make 3 and 4 ones that we come back and do. I don't know. We'll do one more example and pick a more complicated one. And then we'll make these exercises we come back and do when we come back. What can you prove if it is known? Should we do 12? Just trying to look for an interesting one. Or 11? What do you guys like?
Don't know yet.
Look through and pick one that you want me to do. I'll start erasing this.
I like 11.
Do 11.
You like 11? We'll do 11. What can you infer if it is known that A is not equal to 0 and A times 3B minus 8 is equal to A? So, if A is not equal to 0, then what are we going to prove? That, well, let's just start writing out. I wonder if I have a mistake there.
Yeah, I don't get it.
No, I'm wondering because the numbers aren't coming out nicely. Is that supposed to? Oh no, it's coming out nicely. Then B is equal to 3. Sorry, had a brain fart. So let's go over that again. So here's ultimately what I'm going to prove. I'm giving you the conclusion that we're going to come to. Prove if A is not equal to 0 and A times 3B minus 8 is equal to A, comma, then B is equal to 3. That's what I'm going to prove. Or in other words, B equals to 3 is what I can infer from this fact. And I'm going to prove that. Okay, so 1, I always start by writing our antecedent. Let A and B such that, A is not equal to 0 and A times 3B minus 8 is equal to A, right? A, not 0 there, A. That's what prompt says, right? Yeah. Okay. And A is not equal to 0. So then, how can I rewrite this right here? I can write that as A times 3B minus 8 is equal to what? A times 1.
Why do we need the 0 bit?
For the next part that we're going to do. So now I want to use axiom 2, and I'm going to conclude, then 3B minus 8 is equal to 1. Axiom 2 tells us for all integers A, B, and C, if A times B equals A times C, and A is not equal to 0, then B equals C. So the only reason I was able to cancel out the A on both sides, if you want to think about it that way, is because we knew that A was not equal to 0.
Well, it can't be.
It could have been. Then we just
Could.
had 0 equals 0, which is fine.
Well, yeah, okay, I got you.
Okay, so by axiom 2 then, we come to this conclusion, right? Rewrite both sides. This is the same thing as 3B plus negative 8 is equal to 9 plus negative 8. Follow that?
Yep.
Now I'm going to use axiom 1, cancel out the negative 8, and we get 3b is equal to 9. I'm going to write that as 3b is equal to 3 times 3. I'm once again going to use axiom 2 to conclude that b is equal to 3, and we're done. Good?
Yeah.
A little bit awkward, and these won't be the actual axioms we work with in algebra. It's just for the purposes of these exercises to get you comfortable working with just a couple axioms. and get you comfortable writing some basic proofs. So that's where we'll end it for today. Any of you who are trying to get credit and you have any homework questions, feel free to stay after and ask me any questions to your heart's content.